I think we are live.
Hey everybody, thanks for coming.
Hi everyone. Thanks for being
Hey,
here.
everyone.
Yeah, welcome. This is the first, I think, live stream of us getting back to the Dat Rust port of the Hypercore Protocol. Yeah, I'm Franz. I live in Freiburg, Germany. I've been hacking on Hypercore Protocol, that project stuff for, I don't know, about 2 years now. And about a year ago, a bit more, I started to learn Rust. And as a first project to get into it, I took up trying to continue the port of the Dat Rust, the port of the Hypercore Protocol stack to Rust. Yeah. I'm here today with Carissa and Friedel. Maybe you want to say a few words?
Yeah, I can just say hello everybody. I started learning Rust about a year ago. I've been working on that since basically the beginning in 2014. And I'm just really excited to see these come together, Rust and Dat, which has historically been in JavaScript. I think it'll have a lot of benefits for long-term stability of the ecosystem and these awesome ideas.
Hey, everyone. Yeah, I go by Dig on the internet. I have actually never hacked on that, so this is new to me, but I have been hanging out with these two for a while now. And I've been writing Rust for a while now. I actually don't remember how long, but I did start writing async Rust a lot in the last 2 years, close to mostly once Futures.3 landed, but a little bit earlier than that. And I'll be hanging out and giving tips and ideas where I can.
Yeah, it's really great to have you around, Friedel. We've been working on Delta Chat, but like in different parts of the world, and we only met up once. It's really nice to just could reconnect.
Yeah, especially when we can't do that in person these days.
Yeah, that really looking forward to being able to do all this in person again. So, yeah, how do we get started? I think I'll start sharing my screen, and then I think I just start by going a bit over what Rust crates we're talking about here, a bit what's the state of things, and then I'd say we just start looking into the code a bit and see what we're doing there and what's going to be next, and so on. You can join in and ask questions, or if you have ideas or anything, in either the YouTube comments or in we have a Discord channel. I'll just quickly share a link to that also in the, or is it already? I think it's in the description already. Or not? I'm not sure.
Yeah, so the one of the things that kicked this off is that we got a grant from NLNet to implement Dat into Rust. And so a lot of the Dat Rust implementation before was done on a volunteer basis. And our hope is now to kick off a new development cycle and release cycle, and release at the end of this, next 6 months, release a 1.0 version. So this, hour and a half or 2 hours that we're doing here now is just to catch up and look at the code and see where the state of everything is, do a little code review, and see if there's any structural, architectural things we need to change about the current implementation before we start implementing new features.
So I'm about to get my screen started. Just 1 second. There it is.
Dignifiedquire can come back now. He said not clicking a link is hard. I have to add him back to the stream.
Is that it? Yes, I think so. Okay.
Can you add Frando back to the stream, friend?
Oh yeah. Oh, that's me. Yep. There he is.
Yay, I'm
Hello.
back.
Cool. Okay,
Sorry
so
about
I think you should be able to see my screen now. All right. So the Hypercore Protocol stack is quite a bit of okay. So back in, I think, 4 years and back now, 3 years ago, Joshua Weitz started the Rust port of Hypercore. Hypercore is the basic module, the ground module of the whole stack. It's an append-only log. I won't go into much details right now, I think, on the architecture of that.
Yeah, we can assume that people know something.
Yeah, we'll assume that people know something. So, that module is already developed quite far. You can create feeds, you can append to feeds, you can get back the values from the feeds. What is missing from that crate when Josh stopped working on it is everything that has to do with networking and replication. And then I started about a year ago to look into that, and I wrote another crate, which is Hypercore Protocol. And that's the wire implementation, basically, of the Hypercore Protocol. So it does not care about how you find peers or how you connect to peers. That's the Hyperswarm modules. That's up next, likely. But this implements if you want to replicate two hypercores and if you have a connection between two peers, you can use that module to set up the protocol stream, do the authentication, and the encryption. And
is this also using noise?
This is using noise, yeah. So the
cool. So that's the new version.
The high-level interface on that module is, I think in the librs there's an example. Should I increase the size of this maybe for the stream? Like this maybe. So if you have some connection to another peer, you can then build the protocol, which sets up the basic parameters. The only required option for that is this isInitiator Boolean, which is needed for the setup of the noise handshake. So you need to know if either you started the connection or the other end started the connection for the handshake for the state machine to be set up properly. And then this module will do a noise handshake and then start the actual message exchange, which is protobuf encoded messages that go back and forth. And the Hypercore protocol has channels. So usually for each feed that you're replicating with a peer, you will open a channel, and that has built-in security in the way that a channel is only opened between two peers if both peers know about the feed's key, the feed's public key. While only exchanging the discovery key, which is a hash of the public key, up front. Yeah, that's all done and working, basically. Or, well, if it's done is to be seen, but it's working. And the current interface on this is that the this protocol struct, which is returned here. Maybe I go into an actual example so that there's syntax highlighting. I don't know why I had syntax highlighting on the comments here, but it's not working apparently. Maybe that one. Yeah, so let's use that one. So this protocol struct here is takes this stream variable, which is a async read plus async write. Any struct that implements async read and the async read and async write traits, which are the Rust abstraction over a duplex stream, basically. That's how you'd call it in Node.js. So you can read and write asynchronously binary data. And that's like a TCP stream, for example. So all the crates in here, when we're talking about async networking or I/O, are using the async STD runtime, which is one of the two major Rust async runtimes. Yeah, so this struct is built, and then this connect method here consumes a async read and async write struct, and then you get a stream. So stream in the sense of Rust stream trait from the futures crate. So an async iterator, basically. And you iterate over events that are emitted from the connection. And the events, there is just 4 at the moment. The handshake event is emitted when the connection setup is done and the peer both peers completed the noise handshake, so you have a secure connection. Yeah.
Just a quick question. So is the idea that we're going to go through the Hypercore Protocol crate and see if there's like improvements to be made to it, or like architectural? Yeah.
So
okay.
Yeah, let's
do a code review
in
or
a second about how we gonna do this. Yeah, maybe let's skip some details for now and first get to the bigger picture. So yeah, but I'll just quickly go over this example here, and then I think continue with the other parts, and then we'll talk about where we actually want to start. So this protocol struct here emits these events, or you iterate over the events, where the most important one is the channel event, which again emits an async iterator. So this channel again is an async iterator, where you iterate over the messages from one channel, so from one feed. And this is then where you'd actually do the where is it? The actual replication logic. Like this is where you'd receive the messages of I have this data, I want this data, and then exchange the actual data blocks of a hypercore and set some options, extension messages, and so on. But this part, like dealing with these messages, is not implemented in this crate. So this crate deals with connection setup and gives you these 2 iterators over the mainstream and then the substreams for each channel. But what you do with them is not implemented in here. So that's one of the points we likely want to talk about. Where should that live, and how exactly we go about implementing that part?
Any initial thoughts here?
Yeah, well, I took a stab at starting to implement this. And so back about a year ago, in the Node.js implementation of the Hypercore Protocol, Matthias and Andrew and Paul and so on went on to implement something new, and that's called the Hyperspace daemon. And the Hyperspace daemon basically is a daemon, a little server program in Node.js that manages storage and networking for hypercores, and then exposes an RPC interface on top of that with a custom small RPC protocol called HRPC. And I took a stab at implementing that because I think in the end, implementing like a Hyperspace daemon in Rust would give a really nice surface to get all this usable from both like natively in Rust and also then back into other languages like Node.js, because you can just connect to the daemon and it would expose the same interface as the current Node.js implementation does. So that could, if this all is finished, allow, for example, Beaker browser to just use the Rust implementation, because it only needs that daemon to be running. And in there, so this Hyperspace repo has a number of subcrates, and those are like quite experimental at the moment. Like I wrote that with the idea, okay, I want to try to how could that like all be set up in Rust, and got to the point that most of it somehow works. But I'd say that one of the major things that we could do today is look a bit about like the architecture of these crates. Does this make sense to continue to build in that way, or are there better ways how to structure that, and so on? So at the moment, there's 1, 2, 3, 4, 5 crates.
Just a question there. So is the idea that effectively at the end, if you put these crates together, you have this Hyperspace daemon, or like everything you need to have that Hyperspace? Was it called Hyperspace daemon? I lost.
Yeah. So this server crate in the end has a binary that you can run that would that opens a socket where you can connect to with the RPC client, and then you can create hypercores and enable or disable replication, like announce or unannounce them on the network for replication. And you can also append data to hypercores or get data from them. So
and the cool part about that is that all the apps that are currently being written on Hyperspace would, in theory, not have to change anything.
Yeah, exactly.
Right. That would expose that HRPC layer.
Yeah.
Exactly. But I would say that aiming for that binary daemon that you can run and then use like also the HYP command line tool that the Hyperdivision folks recently released, you could then also use that to talk to the daemon. At the same time, I think the architecture of this whole stack should be so that all the modules that are one layer below are like have a well-designed API to make them to use them directly, like in a binary or in a library that would not want to use the Hyperspace daemon. I still think that's like a question that has like pros and cons, whether for your application or so you want to depend on the daemon to be running, or you want to do things natively, like for small tools. It could also be nice to have everything included directly.
Yeah, there aren't that many, peer-to-peer implementations of protocols in Rust. So I think it could be an interesting option for some apps who are looking for a native implementation in Rust of some of these primitives.
My connection is back. Okay, good. So right now we have these 5 crates in here. So this common module just contains the protobuf schema for the RPC connection. This is copy pasted from the Hyperspace RPC Node.js module. Likely a bit outdated as it's not been worked on since about 6 months, I think, or even more by now. And then this server crate is what brings it all together, basically. So this crate starts the RPC server, starts the networking. We got to talk about that too. The Hyperswarm implementation. I don't have this in here right now. Let me just quickly copy that over. And then this core store crate that doesn't have to live in Hyperspace. That should likely be a proper crate of its own. Is a port of the Node.js core store module, basically.
And that's for managing multiple hypercores.
Exactly. That's for managing multiple hypercores. So let's have a look at the high-level API. So you open a core store and you give it a path, like where the hypercores should be stored on your local file system, and then you can open hypercores either by their key or by a name, and then the name will be derived. The key will be derived from a master key. That's a feature of the Node.js core store too. And if you have already opened a feed before, you can also get it by its discovery key, but only if you opened it before, because the discovery key always is a hash of the feeds key. Yeah, so it's basically a quite straightforward port of the Node.js implementation. So you have this to deal with multiple hypercores. And then, oh yeah, the networking. Just give me 1 second. I gotta get that into here. So the networking part is what would set you up, give you connections to other peers, right? It's the Hyperswarm DHT, as written by Matthias mostly in Node.js. And so another Matthias, not Macintosh Matthias, took a stab at porting that to Rust. I think I'll give a link to that repo because it's not in the main Hyperswarm. That's it. And I'm actually not really sure in how finished this is at the moment. Matthias started to work on it, and I think it basically works. And I tested it and got some positive results, but then also sometimes it failed, and I didn't really look into that. So that would be another big part that we should talk about, likely how to continue with that. But if you have that, or if you assume that is working, this basically, the Hyperswarm DHT, you give it a discovery key, and it gives you back peers like TCP connections or UDP connections to these peers where you can exchange data on. And then back in here, this server crate is what sets up the DHT. It sets up the RPC connection, and it sets up a core store. And then it tries to plug it all together so that the whole flow can work. And right now, there's one other module in there that's called the Replicator, which is this part I've been talking about before, that would connect the core store to an emitter of feeds, the core store to the networking side, and would use the messages for each channel of a protocol connection to a peer, and have a core from the matching core from the core store there, and would then do the actual replication logic, which is very partly implemented only at the moment. I think it's in here.
Which async libraries are you using here?
So this is using the it's the channel, the multi-producer single consumer channel from the Futures crate at the moment. By now, there's also a stable async channel implementation in async STD, which I think has a few features that might be nice to have. So likely we'd want to switch that over, but for the basic flow wouldn't change much. The API is basically the same. I think you open a channel and you have a producer and the consumer side of the channel, which can be on different threads or in different async contexts. And
Prudel, do you have any thoughts on that?
Yeah, the channels that we have in Async stood in 1.9 now are finally stable, and so I would recommend using them. The only issue with them is they are currently, we don't have a many. Well, we have if you need to have events delivered to all of your consumers, so broadcast was the word I was looking for. We don't have broadcast channels currently. I don't remember if the Future Squared actually has a broadcast channel. I don't think so. There is an implementation that can wrap other channels to implement broadcast, which I've used in the past. I think it's called Async Broadcast or something like that, which works reasonably well. But I don't actually know if you need broadcast in this context.
Yeah, I think we need it. I at least two at least two places here I implemented like a very rough broadcast channel that would just allow you to subscribe, like the core store crate, for example, has that to inform the other parts when a new feed is created, so that it can be shared. And it's very simple. Let me just check that if it's in here. Yeah, so I just the core store struct at the moment just has this vector of channel senders, and you can subscribe to the core store, and it would return the receiving side of a new channel that's created. And then there's this emit function that would just send a message to all of the subscribed channels, which is like a non-optimized version of a broadcast channel, I think. Switching that out to an optimized implementation certainly makes sense. But I think feature-wise, it would basically be the same, right? So this emit method just sends a message to all subscribed channels.
Yeah. By the way, I'm just seeing the bounded channel thing here. We do now have, so one thing that the old async channel implementation didn't have was unbounded channels, because there was an initial design thought that this is really not actually what you want. But it turns out there are definitely places where you want to use them. You should be careful though with unbounded channels.
This 100 here is a random. Yeah, this 100 here at the moment is a random number. It was just a random guess that would of course have to be thought through. Like, I think the risk with unbounded channels could be that if like the receiving side doesn't accept the messages for some reason because it's stuck at some other place or whatever, then you just fill up your memory with messages forever, right? If they are coming in from the networking side.
Yeah.
So there's a little to-do item there.
The question is really like, I don't know yet, is how much worth it is actually to, like, this works now as a broadcast construction. So the question is, how many events are you actually pushing through here, and especially how many subscribers do you actually have? Because if you have like 10 events per minute and 20 subscribers, then it doesn't really matter if you push some highly optimized broadcast channel into here. But if you have hundreds of events per second flowing through here to many subscribers, then that certainly makes sense to optimize.
Yeah. So right now there wouldn't be many subscribers, I think. Maybe we go into this the place where this all is like plugged together for a second. And this is this listen method in the Hyperspace server crate at the moment. So this opens a core store, and that's happening at many places right now. The core store is wrapped in an arc mutex so that it can be shared safely between different async tasks. I did that a lot at a lot of places in this Hyperspace implementation here, because it just felt the easiest to get started, to just basically whenever I need to share a struct between different tasks, I would just wrap it in an arc mutex, which I think is nice to get started, but also feels a bit cumbersome then at times to always write arc mutex and to always wait for the lock and be careful to not keep the lock for too long, like only keep it for exactly what you want to do. I would.
Yeah. There's a slightly nicer construction to this usually. Unless the core store is actually used in a place where you don't want that, what I usually do is I create a core store and then an inner core store, and then the inner thing is just wrapped into an arc mutex, and the public API basically just proxies things through, taking care of blocks. And then if you have a lot of methods that actually only read and just a few that actually need the write access, what I do is I switch from a mutex to a read-write lock. And that way you can expose a nice read-write based API, and they only take the kind of blocks that you actually need, optimizing that a little bit. And depending on and this nesting works reasonably well. Sometimes you actually don't need that, and you only need to wrap some properties of the inner thing, but that all depends on what you actually have in that struct wrapped up.
Cool.
Yeah, I've seen that at a few places already, and also that would be what I would I think recommend to do, just the same. For those following the stream, I've been writing down this pattern really quickly, so maybe that's easier to follow along, and that's happening as I'm seeing it a lot in Rust context, that you just hide the other advantage that a question like Dig just raised, whether you want to use arc mutex or an RW a read-write lock, is then an implementation detail that is not exposed in the public API.
Exactly.
Which is also then a good, yeah.
One other really good thing about this is that it takes care of you can hide the lock durations such that you don't have to worry as a consumer about keeping the lock too long, because it will only always get released when those methods end. Yeah,
that
cool.
should be quite straightforward, I think. And then you would also lose that line everywhere and leave that concern up to the implementation and not the consumption side of the struct.
Cool. Thanks. I wrote that. I'm writing stuff down.
Cool. Thanks, Carissa, for taking notes. Yeah. So to continue on that one here. So the core store is created. Then this replicator struct that I've shown before is created, and then those two are currently here combined in a state struct that just to pass them around together. So I was also thinking maybe that replicator stuff could live directly in the core store later on, because maybe there's no point in having too many crates around here. And then this is the main part I wanted to get at. There's 3 tasks being created. So a task, for those following along, in async std is a group of is one task in this here will then usually be one loop that loops over something that emits messages or so, and through this future join all down here, all these three tasks are run in parallel. So it's basically like threads, but it's a lot less overhead than threads because they run as lightweight tasks that have cooperative scheduling between them. And the three tasks are, this down here is the RPC connection. So this gets this state struct. It basically, I think it only needs the core store. No, the replicator is also needed to set one core up for replication or take it out of the replication again. This one here is the networking thread task, which would listen for events from the replicator and for events from the DHT, which is created in there, and then match them together. And the third one is this replicate core store function task, which my code navigation is not working. Why did it break again? So this replicate core store function is in here, and what it does is it listens for events from this replicator struct. This is again this subscribe broadcast channel pattern that we've seen before, and whenever the replicator emits a discovery key event, so this will happen when the other side, a peer you're connected to, wants to open a feed, then it will send over the discovery key. So this is the basically the same event from the Hypercore protocol that sends over a key. You would look if you know about this key, and if so, you'd add that feed to the replicator. Maybe that wasn't the best place to get into that because it really depends on this replicator struct. Let me just quickly. So where is it? Sorry, be right back. Okay. Yeah. Where is this created? Sorry, I'm just, yeah, it's this yeah. We should look into this replicator struct first, because that's actually the main loop and logic around connecting all these parts. Yeah.
Oh yeah.
So this replicator struct basically manages the ongoing replication of a number of hypercores and a number of peers. So you have this N-to-M map basically between peers and hypercores here. So say I have locally 10 hypercores, I'm connected to 5 peers. If all of them can have 0 to n of these hypercores also, and for each peer, for each hypercore that we both know about, there will be one channel basically where you exchange messages with that peer in relation to that hypercore. And it has this main loop. Yeah, it has these two main methods that are called from either the DHT or the RPC layer that controls which feed should be replicated. and you can either add a feed. So this is a Hypercore, the feed struct from the Hypercore crate. And here the streams, so the connections to another peer, the actual I/O connection, TCP connection, is added, and then this Hypercore Protocol struct is being created, and then this run peer function is the actual main loop I wanted to get at. So this task here that's being created here, so there's one task for each peer and one task for each peer, and you have the, sorry, I have to quickly look into this for myself. Yep. So we're dealing with two iterators here, two event flows. One, I have the connection to another peer, which is transformed into this Hypercore Protocol connection, which emits the protocol events. So this is this proto events here. And then we have the replicator events, which will tell us if there's a new feed being added to the core store or to the replication in general. If I say, okay, now I want to share that feed too, this will be emitted here. And then what I'm using here is another pattern that we maybe want to look into if it's fitting. I use the futures stream select function, which basically merges two streams. So both streams have to emit the same messages, the same struct, and then if you iterate over that, you basically get whatever comes next is incoming. And so what I'm doing here is that I have an event enum that is defined in here, I think. Yep. So we have three kinds of events. We have either the protocol events, and this is directly the import from the Hypercore Protocol crate. So the event struct defined in the Hypercore Protocol crate that has this discovery key, handshake events that we've been looking at earlier. And then we have the replicator events, which is defined in here, that basically just tells us a new feed is added, or the network has an unknown discovery key. So someone wants to open a feed that you don't know about, and that you could pass that out to like some upper layer that would look into your local collection of hypercores and maybe check a setting or something if you want to share that. Yeah, and then down here where we've been, these events that either are the replicator events or the protocol events are their respective origin streams are mapped onto that event struct, so that we have a single struct enum, a single enum that represents both of them, so that we can then merge those streams to one stream. And this is then the main loop for each peer. When the handshake is complete, this would share all. Oops, what happened there? All feeds that are currently in the replicator with that peer, right? It would try to open a channel. This will not send that key over to the peer, but only the discovery key, which will then reply with a proof that it knows the key for that discovery key, and then can go ahead and open the connection or drop the connection if the peer doesn't reply with a proof of knowing the feed's key. And when a channel is actually opened, we have this struct here, which will likely be quite important because that's that peered feed struct. That's that one in here. Is where the actual replication logic would happen, right? So this has a feed and a, where is the peer? Here, the channel. Oh, it's not on the struct because it's moved into a channel. But this has a feed and receives the protocol channel for each peer that it's shared with, and then here would like have, what's the difference between those two structs? That's basically a wrapper around that. Yeah.
Which is a wrapper? Sorry.
Yeah, that peer struct here that has one feed and one channel. So it's the
Yeah.
the connection between one peer and one feed, and that would then keep the logic. Do I want to change data with that peer for that feed? What does the other feed request from me? And has the actual replication that would be down here. There's an on message handler, and then this is implemented very, very roughly right now. It can only like send want and have messages and then exchange data messages. So this is one of the major to-dos to get this actually like usable, because there's a lot of optimizations and behavioral things going on in the Node.js part for that. And this one up here is on-the-fly abstraction, I'd say, that would manage these peers per feed. This right now, again, uses argmutex for all the things, because you want to be able to, like if actual data is coming in, you lock the feed, append the data or insert the downloaded data and unlock the feed again. And this will just run forever right now. So you have the tasks being spawned, and then you just wait for that method here. Yeah, and yeah, and all these then are just running forever until I think one of them errors. Then the join all future would fail, and an error should be returned, which is not right now, but that's like, oh no, the join all doesn't fail. We'd have to collect the results and check if there's an error to error out likely.
Yeah, you're not checking any return values there currently.
Yeah,
One note on the spawning here on the join all. You don't actually need to use the join all method here, because you have a fixed number of 3 in this case, and you can just use for a compile type fixed number of futures. You can always use, I think it's called join and async stud. Futures has a similar construction where you just say a. Yeah, so on async stud, a future has a method on it called join, which you can call. So future a dot join future b, and the output of that will be in your future. And so what you can do here is create task 1, task 2, task 3, and then you just say task 1 dot join task b dot join task 3.
Nice.
And the nice thing about that is that you don't do any and you don't actually need to allocate a vector, and it's a little bit more efficient, and also a little bit clearer, because with a vector you always, the assumption, like when I read code like this, is like, oh god, they're going to be like a dynamic number of tasks to be run or something like that.
That's helpful.
Yeah, exactly. You can just chain that at the top.
Yeah.
One long thing, and then dot await to do the thing.
Cool.
And then there's also try join, which is similar, just but it will break everything up. So then you have to return a result, And so if one of them errors out, it'll kill all of them.
Yeah.
Which is likely what you want here at the end, if you actually return results there.
Yeah. Yeah.
Cool.
Yeah, that sounds good. Yeah. Yeah.
And then you can remove that tasks, I think, on line 61.
Oh yeah, sure. Right. Yeah. Mm-hmm. Yeah. So this was this main replicate task. Then the next one is the networking tasks, which uses the Hyperswarm crate to set up the DHT, and then again has a loop over events from the DHT. So this emits whenever you found a peer for a discovery key you're interested in. And then would add that stream to the replicator, which would then open the connection and exchange all the feeds on it. It doesn't actually, it's not, so that's the same as in the Node.js implementation. It doesn't actually care on which topic you found a peer. You don't even know at all times, because the Hyperswarm DHT will just give you connections to a peer, and you will not know necessarily over which discovery key, over which DHT topic you actually connected. With whoever is like connecting to your open port that you open, that is being opened for incoming connections from other peers, you would open a Hypercore Protocol connection, do the handshake, and then just start announcing or offering all the feeds you have right now to that other peer. The other peer would do the same, and you would start to exchange messages only for those feeds where both of you prove that you know the public key for. So this is why here it's just the stream being added. There's no notion of the DHT topic that we cared about. So this is the one loop. It waits for peers from that are connected to you, and then adds those TCP streams to the replicator. And down here, it's listening for these feed events from this replicator, where we've seen that add feed method before, and it would configure the network accordingly. So this to do here is, again, right now it just would announce all the feeds that you have in your core store to the DHT. That should of course be configurable, and there's the RPC API for that. That's just not implemented yet, where you would call like network.configure with a discovery key, and then announce and look up options for either true or false. Yep. And then again, all the tasks are awaited down here. Again, these could likely be just joined.
Yeah, you'll definitely want to join them, because if if the first one hangs, for example,
yeah,
you like the shutdown behavior gets just really weird if you have these spawn tasks. So you'll want to join them all together to make sure that they're properly canceled.
That's helpful.
Yeah. So this code down here is copied from Matthias's examples in the Hyperswarm crate. Yeah, I haven't digged deeply into those. Again, loop over the DHT events and the announce and lookup commands, and inject them into the hyper DHT struct, which comes from this Hyperswarm crate. And there's certainly things missing here. The biggest likely being one is we will have to check and test and try what actually is working fine in the Hyperswarm crate and whatnot. And the other thing is right now we're only opening TCP stream connections to other peers, whereas the default behavior in the Node.js implementation is to open so-called UTP streams, UTP being a protocol based on UDP that's coming from the torrent ecosystem, which is basically a order delivery protocol on top of UDP, which makes it usable over hole punchable connections through routers. This is missing. So this will not work to connect to peers behind routers or to peers that don't open TCP connections from the Node.js side. Right. Just quickly have to plug in my energy here. Yeah. So one thing I've been wondering in this design. So we have all these different tasks that have basically parts of a global application state shared over our comutexes, and that all of them basically have a big loop with maybe some sub loops that are again moved into tasks around async iterators, async streams. This is like the design I kind of went with here because for me it was the most straightforward to implement based on the hypercore struct where the actual like data persistence is happening, because that's using async methods. Like it exposes an async methods as its main API interface, which at some point will be called from all these different parts. Like either if the RPC connection wants to append something or get a block, that's an async method on the hypercore struct, or if the network receives data, same thing. So for me, it looked the easiest to model this in this behavior because whenever I'm in these async loops, in these async iterators, I can just call async functions and await them. I know that other implementations of networking and peer-to-peer protocols in the Rust ecosystem at times try to not do that, I think, and have a non-async state machine, basically, at different parts where you inject events and that are retrieved from another part. I think that might have performance improvements, but that was one of the questions where I'm kind of unsure if keeping with that, like that approach with just having all these async iterators and loops and different tasks, for me was a quite approachable code flow because it's quite easy to see what's going on in a way. Whereas injecting events into vectex living on a struct like kind of was difficult for me to get started with, and I was not sure if that's needed or so. Like some people I talked to said, okay, yeah, you should look into peer-to-peer. They are having this state machine where events are injected and different behaviors kind of like receive these events and then alter them or inject new events, and that whole flow is not async, but or has an async interface on top, but in the core, I think has just vectex of message events. Dig, do you have thoughts on that?
Yeah, I have some thoughts on that. So Rust P2P, first of all, props to everyone who's worked on that. It is a pretty impressive feat, especially it was implemented while Futures 0.1 existed only, which means no async await. Is like this is like the bare metal of bare metal in terms of Rust async. It brought from that era, as far as I understand, these design decisions of using vector queues under the hood and a lot of atomic operations and things like that, which try to really optimize the last bits of performance that you can get there. It has a very large drawback that both using it and writing code for it is really complex. You have to get really into these details and understand them really well to make any progress. It is likely that I've not seen a method that is going to match that performance that you get through that one-to-one. But the question is that performance that you actually need? Because it does make the code certainly more complex. Interestingly enough, there is a project which is writing Replicator again in Rust, which tries to not do this. So they go and they only they started basically from scratch with async await syntax available and on Future.3. And it does look much more approachable. Will they ever be able to match that speed? Maybe, it depends. But it is certainly easier to get into the code and to write it and to maintain it. The only larger async applications that I've worked on so far, I've always went with the loop approach and channels. It's really similar to how you would structure flows in Go code, for example. And there's some good work out there on how you can structure these things in Go. And I think they really translate for the most part. So this is also something to look into, like if you're looking for inspiration, how to structure these better, or like what are things you can do and not to do. Because unfortunately, I haven't seen much documentation or blog posts in the Rust ecosystem about these kinds of architectures. But with channels and async loops, you really end up with the same approach that how you use Go routines in Go. And structuring applications like this is not, Go hasn't invented this. This has been around for a while, but they were some that made it really easy and approachable, given the focus of the language. And then with the channels that we have now in Rust and the async runtimes, you can really mirror this behavior. One thing that I would be careful of is future select, and there's async std merge, and there's a couple of other variants. Effectively, every async lib has like their own version of this. And then there's also the select macro, I believe, which lives, I think, in futures. They're all a little bit different, and they all might not always do exactly the same thing that you want. So I would be always careful to read very carefully documentation, especially on race conditions and error handling. What I usually go for is if it's usable, if it works, then I use async std merge, which is an unstable feature on streams in async std, which works well if you have the same type. The future select, as you see here, always introduces this either thing, I believe. And I really dislike that type. It's really useful, but it's also so useless in the sense of if you read this code, it's like left or right, really, what does it even mean? And so, and what I went for in a lot of cases when I had this is define these enums in line really immediately before the loop. So it's clear they're never used anywhere else. They're really just for this merge operation. And then you also don't accidentally reuse them anywhere because they're now really private to this scope. And then there's a nice thing where you can just write the stream.map using the map function from async std, where you just insert the enum variant, and you don't even need to write a closure, right? So .map, yeah, and then you just write no closure, no closure, and now just write event : channel event.
Ah, that's nice. I didn't know about that. That you can don't even need the that's doing like an into map or something. No, how is it working? And you just give it the type.
It's this is probably the wrong word that I'm using. So basically, the event : so enum, an enum variant itself is like a constructor, right? It's like a method, and so you can just pass it in there as like it implements the right function trait, right? Effectively. And so this is the same as if you were just to put in the named function into there.
Cool.
Now you can just call channel events.merge feed events. You might have to import if you.
Yeah, I don't have my VS Code REST analyzer apparently is not working, and I'm not looking into it right now. So we can just write any code without anyone telling what's wrong, which is also nice for sketching code. And then we can just loop over the events or while
let
event is events.next.await, and then we would just match the event on either channel event feed event, and that would go.
Yeah, and we have now 3 events in that line. So what I usually do is, especially on enum naming, I try to avoid repeating whatever the enum is called on the thing. So just event feed, because like this is already in there, and then you get things get a little shorter.
Yeah.
And
nice. Yeah. This is much more readable than below.
Yeah. Yeah, that looks nicer. Cool. Yeah. Cool, but to come back what you've been saying about the general approach to async multitasking.
I would recommend staying with this approach. There's a good benefit of sometimes having some structs like big up like an application struct really like to manage these things, and then to if you organize things well, you're able to reduce the amount of args and mutexes that you need to throw around, which is always good. But in general, I would argue this is a good approach and will work well for a long time. And if you see bottlenecks coming up, I would start optimizing things then. And then it's likely that you would want to only do the hyper-optimized version implementation in a subpart, right? For example, the store is like becoming a bottleneck, and then you go into there and you optimize the underlying parts there, and then everything else is you can keep at the higher level constructions.
Cool.
That makes sense. We have a question. So in the current state, we don't have gnats punch through firewall yet?
Well, we do. The Hyperswarm DHT has that included as a core feature of the DHT, and I think that is also implemented in the Rust version. I'm not super sure in it. I didn't actually, but I think that's implemented. What we don't have, so this nut hole punching only works for UDP, not for TCP. You can't, I think there's no way to have a TCP connection through nut hole punching, because I think the routers only allow that hack basically for UDP connections. And what we don't have is this UTP connection implemented in Hyper Rust. So while the DHT would give you a hole punched port, there's currently no way to then actually use it. So yes, as of now, this Hyperspace code here does not actually use nut hole punching. So it will fail if it will only ever try to open a TCP connection, which will fail if there's a router in between on both sides. Like if one side actually has a directly reachable network interface, it will work. If no side has that, it will not work. The Node.js version, I think by default tries to both open a TCP connection and a UTP connection. If TCP works, it will use TCP. If TCP does not work, it will use the UTP connection, and that would have to be ported. We researched that a bit back in the last summer. There was there was bindings to the C implementation of that UTP connection protocol, which I think is not super nice to get into here. And there was an unfinished port to Rust. We would have to check out if that is by now easily usable. Yeah, and then over here where we do the, like here, we would basically try to do something like this, which does not exist yet. And then we do, like if one of them errors, we'd try the other one likely. Something like that is what we would do, I think.
Probably race on whichever one.
Sorry?
Maybe. Probably race on whichever one actually connects first.
Yeah.
I don't know, but the question is then what do you do if both succeed? Do you use the one that connects first? Or is there actually a preference? Because if there's actually a preference, it might be better to actually start just
preference
one and then the other.
Right?
I'm not
because
sure
UTP
actually.
is faster.
Let me just, we can look it up. Oh no, that was the screen. We can have a look. I think it's in here.
Let's see if we can still do JavaScript.
Yeah, this is the JavaScript implementation. It seems it's opening both.
If it's TCP.
So here's the TCP connection.
And there's the UTP.
Yeah, and there's the UTP, but I think that is emitted from the DHT. So it seems it's opening both. It might be that one of them will be closed. Why is it doing both?
It's in both.
Sounds like it's doing both. Well, this is the listening part, not the connection part.
Yeah, but I don't actually think it's using both, because it wouldn't really make sense to have two protocol connections to the same peer, I think. So it might be that it's just trying to open them both till the end and then maybe close them when this .sockets.add is there socket.destroy on timeout. It seems it's setting up both connections. So yeah, basically we would.
But this is the server. This is the server part, right? This is on incoming connections, so it'll establish incoming ones. The question is the dialing.
Yeah, there was the listen.
Both. So the question is there a dial, like when trying to dial a peer, which one is being used?
Yeah, you're listening on both, and where is the? Well, it's always incoming.
Where does the dialing happen?
The dialing happens. So this is peers that you get from the DHT. Where is decided who connects to whom? I think
it is open to. It seems open. It seems to be the thing.
Yeah, the open method is like called only once when the whole thing gets created, and there you start listening. Yeah, so it's in here. This is where other
No,
peers
that's
would connect to
underscore.
you.
No, there's also a regular open, not a underscore open.
Really? That's rare.
At least there's one that's called, yeah, this dot open.
Yeah, that calls this open method once. It's like a thunk that makes sure that this method is only called once.
Does the actual connection happen on a higher level?
So this module is used by the Hyperswarm module, and let's see how it's used. So this is called for each established connection, either UTP or TCP, and maybe it's deduplicating them somewhere in here, because it actually can also happen that by other reasons you get duplicate connections to peers, and I think this has some way to close them when they are duplicated.
Which would mean it's a race condition, right? That it just uses the one that connects first.
Yeah, I think so. I'm not like, I think we skip that for now. We can also ask Matthias about it. If I remember correctly, there was some point where it would deduplicate the connections again, like it would detect I'm connecting to that peer already, and then close one of them, likely whichever came first would be kept. I don't think there's code somewhere that would actually try to find out which connection is like faster or something. So yeah, likely we would just do both of these at the same time.
Yeah, and then use the one that succeeds first.
Yeah, so we would I would have to look up what's the nicest way to have them run both. Either we would have to spawn two tasks, or
no, you just connect dot race and then the other connect. There's Async has a race method which you can use to race two features against each other, and it will return the result of the first one that finishes.
And then it would be some either left or right thing. Likely.
Yeah, there's something like that. Yeah, check.
Matthias says it's whichever connects faster. So
yeah.
Just race.
Yeah. They have to return the same output, so you have to map them to some.
Right.
There's also try race, which might be what you want, because it keeps going if one of them returns an error, which is really what you want here, right? Because if one fails, you want the other one to try to finish, and not return the error, actually.
It's unstable, though.
Everything is unstable. Everything merge is also everything cool is unstable.
So you'd recommend to just use the unstable feature flag in async STD?
Just use unstable.
Okay.
Yeah, you might have to do some work on an upgrade, but these things are like they're not gonna go away.
Yeah, I think that's all right. There's lots of unstable things in this whole thing. Cool. Anyway, all this is kind of coding into the blind here because we don't have that UTP stream .connect. There is a crate. As I said, I checked it out quite a while ago. Yeah, it's still unchanged. 4 years old.
Probably
so likely it is not really finished. But maybe if we're lucky, the actual protocol logic is implemented already, because the roadmap here has quite a few checked boxes.
That looks actually pretty impressive.
Yeah.
Maybe
I
it's
didn't try
just
it
a matter
out,
of
so
trying it and then maybe adding some missing things, but this looks pretty good.
yeah. I think the API is just like it's exactly what we need. So we can just try it out.
Well, not quite what you need, because this is a sync implementation. If you look at uses standard IO, right? So I guess there's some work.
Yeah. Well, we could likely, but then we could like move it into a task plus channels on top for each connection, but likely it would be faster and more efficient to actually look into the module.
Yeah, that gets really annoying with the writing and reading.
Right. Yeah.
I've done wrapper things like this, but they're really painful and hard to not get wrong. But it depends on the underlying implementation. Like, it might be actually very easy to move to an async.
Yeah, that's actually one of the great thing about Async std, right? That it actually like mirrors so much the standard library, the sync standard library, that you might get away with just sprinkling in asyncs and awaits and hoping for the best.
Yeah. It'll depend on how they actually implement the underlying stuff.
Yeah.
What socket? Yeah, what are you doing there? Socket
UDP socket.
Right. So you can just use a regular UDP socket from the async std UDP socket under the hood for that, and then probably do some mapping on top of that, and then you might get actually away with this pretty straightforward port. Oh, you also need to update some things. It's still using the try macro. That's an indicator that
oh wow, that's really old.
It's pretty old, yeah.
Oh, there's ongoing developments in other repositories.
Oh, nice. Oh, might be useful.
Archived.
Oh, but it's archived. Oh, that's unfortunate.
Interesting.
7 months ago. Oh, this seems to be.
Oh yeah.
Somebody
start
tried
converting
to
tests and example to async. So someone took a stab at it with Tokyo, though.
Yeah,
but still, that might.
This future 0.1 or 0.3?
Future core 0.3.
Yeah. Oh, that might be useful to look at.
Cool. And there was another one.
Castello
that one
Labs.
Yeah, I think that Sonic Frog had. I think that Castillo Labs has just one commit, but that one has quite a few.
This is not async.
No. Oh, it's not the right. It was not the branch. It doesn't take your GitHub to the right branch when you click it. You have to check here. Update.
Sonic Frog.
Yep, that will be next.
This is a Castello Labs one. I think you want to be on the Sonic Frog one. Right?
Yep, I think so.
Yeah, Sonic Frog.
And what was the branch?
Update.
Async.
Oh, async?
Yeah.
Okay,
cool. That's promising, that name.
Cool. Let's check what it's using. Took you again, but also.
Futures.
Tracing. Tracing is good. Yeah, but I mean,
Yeah.
Switching between Tokyo and async state is like, it's very, like, the amount of work is usually very small.
Yeah.
Yeah, and it's not using anything special, right? It's using the delay there. No, that's fine. Channels, unbounded channels. Yeah, you can just switch and replace those.
Yeah.
But
cool.
Yeah, you'll have to make sure to audit the poll methods, because I don't know them, so I have no idea. They might know exactly what they were doing, or they might not. And I've written a lot of poll methods, especially when converting sync to async code, where some subtleties just were screwed up, and then things broke. This is unfortunately still the hardest part of like implementing anything instead in async. In Rust is if you implement poll methods manually, it is very easy to get something wrong, which creates very subtle errors. Like the basic things work, but then some subtle things break.
Yeah.
And it's oftentimes, unfortunately, not very obvious.
And also there's this, like what I've ran into quite a few times is that if you have some code paths that use async methods, and then for one reason or another, you want to manually implement a poll method, for example, to expose a stream interface, which right now you can only do by implementing a poll next method, then you have the thing that it's still quite unfortunate, I'd say, or well, not unfortunate, but it has quite some overhead to then call async methods from there, because you have to store the future somewhere, and that works, but you have to deal with pinning. Like, for example, here in the Hypercore Protocol crate right now, I'm doing also something that is likely not there to stay, because I went with this, like, let's just use async methods because it's the easiest design. I have this pub async fn loop next here,
right?
Which is on the struct. It has a mutable reference to self here, and on this protocol struct we have where is it? Here. We have these reader and writer structs, which are basically just the async read plus async write, split it into the reading side and the writing side, and then they are wrapped in a buff writer and buff reader, which is good for performance here because we're sending out many small messages, and that makes, I think, it more efficient. And then this protocol reader and writer are that's the basic. It does the crypto and the not the message passing, but like emits single messages out of the continuous binary stream.
Right.
And then in that I have this where was it? Here? No, not in it. This async fn loop next, which again does something that I really don't like right now. I actually have a version that removed that. So this is right now using the futures select macro, and I would not recommend that. And I already, like, I have a branch there that got rid of it because it really messes up all your error messages, for one. So the compiler error messages that are created in here are really horrible. Also, you run into some limits of things being nested. Yeah, it's not worth it, I'd say. And
I suspect that and you would need to look at the whole method, obviously, to be sure. But I suspect it might be actually easier to not use an async method and actually do the work of implementing a manual poll method. You don't need to you will need to store the futures, or you will need to call, actually, for buff reads and writes, you can just call the poll versions of those methods, right?
Yeah.
Which, like, combining poll methods actually is not that bad in my experience. So if you have things that expose everything that you need as poll methods, then it's fine to put them together. What gets painful is if you have interfaces that don't expose the manual poll things, and then you have to poll the future instead of the poll underlying stream thing.
Yeah.
And then things get hairy. There's some patterns that make this easier, but it's still every time very tricky, I think. There is one project that might be able to fix this, and I have written once a prototype which was really fun. So there's a crate that gives you a macro for writing generators. So generators are very unstable, but they are used under the hood to implement async. Now they're not exposed, but because async await uses generators under the hood through the compiler, what this crate is doing is it uses async await not for async await purposes, but to build generators. But you can take this to a next level, and I've actually have a prototype where you can write in a generator, like how you would write a stream in JavaScript, using a generator. Async iterators, I think they're called, if I remember correctly, right?
Yeah.
You can similarly write then a stream in Rust, which is really promising, and would be great if this eventually ever makes it properly into the language. But it's something to look into if you want to have a fun experience. It's not I'm not sure if it's something I would use in an actual project, but it's very interesting at least.
Cool. Maybe you could paste a link to that. I'd be keen on checking that out. I started here with that pub async fn loop next because it was just the easiest to somehow get started, and then I realized that select macro that I don't want to use it, and also in that first version to then have a stream interface on top of that. So because to have all the combinators that the stream brings with it and so on, I wrote something that would wrap that struct. And
did you see Substack's comment? Substack says,
okay.
I've used future stream unfold to implement a readable async stream. Still not easy, but either than implementing poll.
Stream unfold, yeah. So stream unfold, there you have an async closure, right? That is ran for each iteration.
Yeah. Which is almost like a generator thing.
Mm-hmm.
And you have a state that gets passed, that gets passed along.
Yeah. So, yeah, as I said, I started to look into how to. Here I have this version which is semi-complete, which just directly, as you've just outlined, implements the poll next future manually here on the right side, and then how can I? Does stuff like that. If it's a channel like this outbound RX is, it's where the protocol struct receives messages that are to be sent out of one of the subchannels.
Yep.
And then I do this match pin new on and call the poll method of this channel.
Yeah.
And if it's pending, I just do nothing, which means that it goes on to checking the next thing below. And if it has something, it would enqueue this, and this queue is actually a sync message right now. So this is a bit into the direction of what I think the lib peer-to-peer stuff does, but it's not really exposing it. It's just using it internally to store these messages to then send them out, I think, right down here. No, that's the reader. Where's the writer? Here. It just does this, which takes the queued messages and sends them out. So yeah. One thing I think
this makes total sense. This makes total sense to use that to have internal sync, because you need, if you use poll methods, right, implement poll methods manually, you have to do everything sync. You just have to be very, 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 very careful not to block for too long. Otherwise, things will get very sad and very unhappy and bad, to put it lightly. And unfortunately, debugging, if things get very sad, is very hard. Still, we don't like the tooling. We're still much better tooling to find blocked futures and pin down where they're actually hanging. So I have used LLDB a little bit for like just breaking into these things, but it's tricky. Yeah, so you have to be careful, but this is what you need to do, right? You need to synchronously manage them, and this is why you get them into like using lock-free structures like atomics to optimize this, and which is why a lot of the things under the hood actually end up using atomics for some things, or you use mutexes, but mutexes are much more expensive in most cases than atomics. So if you can avoid using a mutex, it's like you really want to avoid using mutexes if possible.
Yeah, the nice thing is that when implementing that manually, I can keep a mutable reference to self around easily, and so for these simple things, I can just directly, I think that's just the vecdeck, if I remember correctly, right here. Yeah. I think for like low-level parts like this protocol implementation, to me it seems that it makes sense to take like this little extra effort to have not async methods here all the time, but try to get that flow running in that way. So that would be from my side one of the next things, maybe to finish that branch. There's not much missing. You have to take care of forwarding there, like what should happen when, and when do you want to wait for that, but that likely makes sense anyway. So I didn't really think that completely through right now. It first waits until everything that needs to be written out is written out, and then checks for new incoming things. Likely you want to have something in there that would kind of try to level that a bit, but yeah, maybe it's also correct.
Level it,
like I was just thinking, if we're exchanging a lot of data, like you're sending data over to me and I send data, receive data from you, this could, like if you requested a full hypercore from me, and if that other task in the replicator just keeps sending messages into here, this protocol stuff struct, this here, this ready make macro does so you try to write a message to the other peer, and until that's complete, you would go out of this poll method and then be polled again when your message is written, and that would be repeated until everything that's in the queue to be sent out would be sent out, and only then it would come to reading incoming messages, which might be fine, but which also could lead to like starvation of the reads. If you're sending all the time, you could maybe never get to reading what you're sending me until everything I'm sending to you is finished. It might be that that's not a problem in practice, because there could be at other layers of the stack, you could also like wait until you get, I think, for example, you're requesting each message in Hypercore Protocol. Actually, each data block is requested first and then sent. So But yeah, that's something like maybe you would do this down here again. Here, actually, it's implemented the other way around. Here, you're not waiting until everything is read, but only what is currently available, and then go on in the loop. Yeah, I think
you probably want to track how much you're reading and writing, and
right.
have some logic to balance this out. This is actually a problem with a lot of read-write clocks, is that some of them have a tendency to either prefer reads or writes. And usually you really don't want to prefer either. You really want to have some balance. So likely, if you could do something very simple, right? You can do like have a Boolean that says like, was the last thing a write, and then you just alternate in the preference. That just makes sure that you would keep a balance. But then you can also be like, just have a counter of reads and writes, and be like, if I have X% more reads and then writes, then I want to prefer the other one, for example. But you likely want to have some logic to make sure that you don't starve either reading or writing. Otherwise, it's very easy to get into some stuck place where one or the other destroys basically the system, because you're just only reading, for example, from the incoming pools and never write out.
Yeah, that likely. I'm thinking, what about just doing it like this, like it's done down here, so that I have the big loop, and whenever it's pending, now it could loop forever, right? Yeah,
This could never
return it someplace.
Right. You don't want to do that, right? You probably wait. When would you return here?
Actually, I think
what you actually want to do is you only want to ever try to write a single thing per loop iteration, right?
Yeah.
So you don't want to actually have a loop there. You just want, if queued messages is not empty, then try this.
Yeah, likely yes. And it returns like it returns down here if there's no queued events, and if there are queued events, it returns up here with poll ready and the event that should be emitted. So it should not, it cannot loop forever. It can only, like, if there are events, they are drained first, like emitted as ready results, and if there are no events, it goes once through this and exits with pending if there was no new events that were created.
Yeah. I'm skeptical of having a loop in there though in general. Like, do you actually need that? I don't think you want that. Because poll should be really, really fast to run, right? So you don't actually.
I think I can just remove that loop completely
once, and at the end, if nothing else happened, then just return pending, right? Because this means, look, we don't have anything right now. Yeah. And this way, you make sure that this returns quickly, and just and then it's the matter of the runtime making sure that it gets called again.
Yeah, I actually think you're very right. It's not needed at all. I can just do this. I just replicate this check if there's events to be emitted or not.
Yeah.
Once at the bottom and once at the top. Because like I don't know if the code in between. I think there are situations that it creates more than one event.
Oh, I see. That it creates another event. Okay.
Yeah, it could be. I think, for example, if a new channel is opened, it could be that it's actually emitting two events. I would have to check that.
You only can ever emit a single event from a single poll call, right? So
yeah, that's why up here, it like the first thing it does is if there are queued events, get them out, and then it'll be called right again because it emitted ready.
Yeah.
Mm-hmm.
That makes sense.
Cool.
All right, folks. I unfortunately have to run now.
Yes.
Yeah, I
Life
also have a
continues
thing
outside of this world.
in 8 minutes. But it's nice chatting.
Yeah.
Thanks for coming and reviewing the code with us and everyone for
Mhm.
watching.
Thank you for inviting me. Thank you, everyone, for watching. This was
Yeah.
pretty great.
Thanks, Dig. It was great talking about these things.
Yeah.
And
I am now in this weird Discord channel because I've not joined enough Discord channels in my life. So if there are
And
more
we
questions,
will-
everyone, feel free to ping me and I'll try to get back
Yeah,
we'll be
nice.
in
at a
there.
reasonable time.
Thanks. Yeah.
And I
Right.
wrote up some notes of to-do items, and some of those to-do items were written in the code. So then I think we'll open some issues on the repositories and circle back in like a month or so and for another live stream. And in the meantime, maybe we'll get some of the stuff done that we talked
Cool.
about here.
Very cool.
And also, like, for anyone watching and still being around, yeah, please, we feel very free to kind of hit us up, ping us on the Discord if you have any questions or pick out an
Or
issue
open
or
pull
get
requests.
started.
Yeah. Yeah, pick up an issue, open a pull request, and
Yeah,
work on it together.
we're very open to it. Like, there's no one like with fixed tasks or so in the moment in there, so we're trying to make this into a community effort to get this usable. I'd be really looking forward to that. I think that could open quite a few doors to make this easily usable from other Rust code. One thing actually that I wanted to mention, if anyone wants to get started or to just play with it, that could be a quite nice starting point, is this client, the Hyperspace client, which is in here. That's really not much code and quite straightforward. Whoop, why is it open this over here? Let's take it down. Which right now just has this append and get method implemented, I think, or maybe a few more, kind of continuing that and implementing just the client-side API is quite straightforward, and that would allow to actually start building Rust apps on top of that by using the Node.js Hyperspace daemon with a Rust client, and then switching over once the Rust server, the Rust daemon part is finished or usable. And that's actually quite straightforward to implement the remaining methods. It's basically just emitting the right requests. It's using that HRPC. So that could also be a good like starter issue to kind of get that feature complete to all the. It's not super much the RPC API. It's maybe 20 methods or 30. Yeah. It's just something that I didn't want to forget to mention because I think it's a nice starter issue also. Cool.
Thank you so much.
Teresa?
Yeah, this is great. Thank you so much, and we'll do it again next month.
Yeah, let's do it again. Cool.
All right, great.
Okay, bye-bye. Thanks, everyone,
Bye,
for
everybody.
joining and watching.
See you in the Discord.
Bye-bye.